All right, so today we're going to do a couple of things. We're going to review all our integral techniques and sort of throw them all together in a nice stew of techniques. And then after that, we're going to leave the world of techniques for a while and go into something called slope fields, which is a lot more geometric. It's a lot more graphical and conceptual in nature. So for those of you, like some people, really like these very computationally intensive techniques, and you'll be disappointed to leave and go into the more graphical conceptual world. Some people like this graphical conceptual world more, and you'll be happy to leave behind the world of computational techniques. Whatever you like or dislike, there is nothing but what is going to happen. And what is going to happen is we're going to do the integral techniques and then slope fields. So next, by the way, you really have to be good at both. You have to be good at visualization. You have to be good at analytical work. Everybody's better at one thing or another, or everybody likes one thing or another. Whatever you're best at, you should capitalize on. And whatever you need the most work on, you should challenge yourself on. That's how everything works. You guys probably already know that. All right, so here we go. Well, I was going to start with the mixed integral techniques. So what I've got is a big slew of integrals. This is techniques mixed review number 1, which I encourage you to have in front of you in either print or digital form. We have 3 handouts today. Mixed review, well, all right, just for this part. I think there's going to be like 4 at least handouts. We have mixed review 1. We have mixed review 2, which is going to be the homework part of this. Mixed review 1 we're going to do now, so you want to have that. The other thing you want to have in front of you is, I've posted this before, I'm posting it again, the summary for integrating rational functions. So I have this both in a text form and a flowchart form. We will use them both today, and we'll see how they work. All right, so without further ado, let's do number 1. So number 1 is 31x minus 1 over 15x squared plus 7x minus 2. So the first thing I want to do is recognize that that is a rational integral. All right, so it's a rational integral. That means that it is form p over q, where p and q are both polynomials. P and q are polynomials. All right, so some people will, very conscientiously write p of x and q of x because they depend on x. However, we're going to use this shorthand. We're going to refer to p as the numerator and q as the denominator. That's a standard thing to do, and it will help us not write out the words numerator and denominator all the time. Those words have always bothered me. Why don't we call it top and bottom? I mean, come on, you have good words, top and bottom. Why do they have to say numerator and denominator? Just because it's Latin and has 7 syllables? All right, anyway, we're stuck with those, so that's what they are. But of course, in math, we'll just call them p and q. All right, so that's what we're going to do with these. Now, what we're going to do is we're going to look at this and think about the p and q in order to determine our technique. So the first run through, I'm going to use the verbal summary here. So I'm going to look at, r of x is p of x over q of x. So I'm just sort of stating all that. All right, so the first thing to look for is so I'm using this, this is a notation I made up. Hashtag q is the degree of q. All right, hashtag p is the degree of p. I made that up. That's not a standard notation, but I got tired of writing out the word degree. All right, so first let's look and see if the degree of the numerator is greater than the degree of the denominator. See how efficiently we can say the degree of the numerator is greater than the degree of the denominator or equal to. So that's our first question. Is the degree of the numerator greater than or equal to? And remember, equal to, you're also going to do polynomial division. And the answer is no, because the degree of the numerator is 1 and the degree of the denominator is 2. All right, so we can skip that step number 1 and we can go down to step number 2. Be on the lookout for k q prime over q. All right, so another way to say that is the p up here, is that a constant multiple of the derivative of the denominator? All right, so these are questions. So another way to say that is, could you do this with a u sub? Could you do this with a u substitution? That's another way to say that. You check these in this order, whatever you want to call them, because you could call them a lot of things. All right, well, let's see if you could do a u sub. So to do u sub, you would always use u equals the denominator. That's the technique if we're going to do u sub on that. Then du would equal 30x plus 7. Okay, well, there's no way I'm going to be able to multiply 30x plus 7 or divide 30x plus 7 by something to get 31x minus 1. Right? I could add and subtract things, but then you get the trouble that you have dx's and du's mixed, and we can't have that. So since, how am I going to say this? Yeah, all right, so I'll just say that, 30x plus 7 is not equal to some constant times 31x minus 1. All right, so that means we cannot do u sub, no u sub. All right, so the short answer to this question up here No. All right. All right, so now, see, we should go step by step here. What are we going to do next? If the denominator factors. Okay, does the denominator factor? Well, let's have a look. Okay, so let's see if we can factor the denominator, 15x squared. So let's write this. Does Q factor? That's our next question. So I'm just looking at these questions, 1, 2, and 3, just looking at those questions. If it helps you to stay organized to do that, 15x squared plus a 7x minus 2. All right, can I factor it? Why, yes, I can factor it. All right, I get 5x minus 1 times 3x plus 2. All right, let's see what it says to do. So it says, if the denominator factors, use partial fractions. All right, for linear denominators, and this year we're going to do only linear denominators, the fractional parts can be integrated simply using ln. So basically this is just telling you what to do once you've decided partial fractions. So I have examples of that, right? Okay, so now we know that yes, we're going to do yes. All right, so we're going to do partial fractions. So the first step in looking at these things is to go through a checklist, whether you go through the checklist literally, specifically, explicitly, or you go through the checklist mentally, one way or another, you're going to have to decide which techniques approach this, and this checklist is a good way to do it. So now we've decided we're going to use partial fractions. In the next video, we'll do it.